Thank you very much and good morning. Thank you especially to the organizers for having me here. And as by way of introduction, I'd like to thank Kane for giving an excellent background to this talk. I'll cover very briefly a few points about orbital angular momentum and where we can carry it into the X-ray region, which is really my expertise in coherent X-ray optics and magnetism. Then breeze through a few older results with the optics and what we can do with it, and to some more recent results from the EUV and XUV regions onto hard X-rays. And you heard a bit about that already in the previous talk. And then leave you with hopefully some thoughts that motivate you to some deep thinking about where we can go from here. So I find this plot from 1836 to be quite interesting. This is William Whewell's so-called amphidromy chart, which predicted a no-tide area in the southern North Sea between the UK and the Netherlands. After measuring the tides around the sea, he found there was this basically zero of intensity in the middle. And in fact, things were swirling a bit around that middle, you can see in this crude plot. So I think it's one of the earliest known examples of essentially a vortex. It's not an optical vortex, obviously. But it was rather remarkable that this kind of essentially phase singularity was even observed at that time. So optical vortices, you heard all about Maxwell's equations and where you can take them to understand. One obvious way to start, I think, is looking at the total angular momentum, which you can split into two terms. This is found very clearly in Jackson chapter 2, if you've struggled through that as I did. The spin term, the E cross A term, where A is the vector potential, and the orbital term here on the right, which if you read Jackson at that time, probably you ignored that part and didn't pay much more attention to it. Nevertheless, it's there. So one of the natural solutions to the Helmholtz equation, the source-free wave equation, are these so-called Laguerre-Gaussian modes, which have a very characteristic azimuthal phase highlighted here, where in addition to this radial term and an amplitude term, this characteristic helical term defines this mode. The Poynting vector completely specifies the field. Here's the lowest order solution with the phase and the magnitude indicated. And a typical radius that goes to something like the square root of this azimuthal phase index, or mode index L, which is an integer. Well, it turns out that these states have been quantized and known that they're quantized for quite some time now. 1936, Beth did a very beautiful measurement looking at just left and right circular polarization and concluded that, in fact, each polarization can be associated with 1 h-bar per photon of angular momentum, in this case spin angular momentum, intrinsic to the light. In 1992, Les Allen came up with a very interesting extension of this. He went through first and second quantization of these Laguerre-Gauss modes that I just showed you, and concluded, in fact, that OAM, orbital angular momentum states, the second term and the total angular momentum J, can be and is quantized naturally in units of LH bar, where L is plus or minus 1, 2, 3, 4, and so on, per photon, which is quite remarkable. This paper had quite a bit of trouble getting accepted. It finally was published in PRA, but it's, I think, provided the seed for much of where we are today. So-called OAM states are now evident and have been measured, predicted and measured in all kinds of waves. I can't possibly count the number of light, extreme, XUV, and X-ray measurements, both from production detection to actual applications. But in the radio region, first predicted and measured by Bill Day, sound, where they're clearly longitudinal waves, it's not so obvious that that might be the case, with electrons and neutrons, in other words, matter waves, and now even atoms and molecules. Those two there are rather interesting because now we have a mass associated with the wave, or the quantized version of that, and also in the case of neutrons, the magnetic moment. There's some nice articles here going back to 2004 and then just a few years ago summarizing this huge growth in the field. So I'd like now to talk about X-rays, and most of the rest of this presentation is really concerning X-rays of some form or another. You might ask, how could you generate these spiral or helical waves? And a very intuitive approach is to make a helical phase plate, a helical staircase. We did so. This is back in 2002, which had consists of a sort of 150 or so micron diameter, 34 micron thick helical staircase ablated in polyimide, that's Kapton plastic film, designed to give a 2 pi phase shift from across this jump at 9 kilovolts. And you can calculate what that would be and make it to order, so that was an easy thing to fabricate. And did an experiment as follows. We put this device in a coherent X-ray beam. This was at the Advanced Photon Source near Chicago. Then after some propagation distance, about 6 meters, we detected it with an X-ray camera. And that's one thing, but you might say, okay, suppose you make this vortex with the intensity 0. How do you know that you really have something interesting? So we did what I would call poor man's interferometer trick. We put a thin tungsten wire, a 6 micron tungsten wire in the beam, and looked at the fringes around that wire, the Fresnel fringes. And lo and behold, after you do some nice background subtraction, you get not only these sharp Fresnel fringes around the wire. This has not been corrected apart from just subtracting the background measurement with the wire out. And this very obvious bifurcation, splitting of one of the fringes. So if you position the wire to put that right by the brightest fringe, it's most obvious. But this corresponds to the L equals 1 h bar, or so-called charge 1 phase singularity. There's another approach. In fact, there are several approaches, but you've heard about also the holographic one, so-called holographic one, which Heckenberg and collaborators pioneered in the 90s. You can calculate what these waves look like, do this all on the computer, calculate the hologram, the intensity, or the amplitude sum, square it up and get the intensity, and then you, lo and behold, see this L phi term come out here, as well as the curvature, the obliquity, or the incidence angle, and that allows you to essentially make any kind of structure to generate these waves that you wish, with some more or less efficiency. We did some experiments with one of these so-called forked gratings, which is straight on, so no obliquity and no curvature, just the L term. Sorry, just obliquity and no curvature in the L term. And these gratings are not very efficient for soft X-rays, in this case about 870 eV, something like 8%, so you have to block a bright 0th order that goes straight through. But to either side, you get the essentially Bragg peaks, the diffraction peaks, corresponding to plus or minus L equals 1. And also in the higher order peaks, the higher order or higher charge vortices. So the structure looked like this. It's a couple microns square made in nickel. This is a scanning electron micrograph. This is a so-called vortex or optical donut intensity pattern. And then you might question again, do you really have the phase structure and the singularity that you expect? So we played another game. We positioned one of these forked gratings next to, on the same substrate, transmissive substrate, another just a laminar grating of the same period. So we'd expect the OAM beam to interfere at the same angle as the non-OAM beam. This is unpolarized light, and get some kind of interference pattern. And in fact, you get back your forked grating pattern. So it worked. It was very convincing to us. I think you've all become familiar with how to do this now. These are just some examples in the soft X-ray region around 2 kilovolts. You can make quite high charge forked patterns, many splittings. So this was for L equals 10. And here's the second order. If you're an expert, you might wonder, why is there a second order, not just the odd orders? It's because the lines, mark to space ratio of the lines isn't perfectly equal. So you do see some. We also went to charge 100. In fact, here's third order and fifth order. You might just convince yourself it's there. So these can be made with X-rays. You can focus them, as we heard very well about in the previous talk. These are spiral zone plates. I know many of you are experts in these now, so I won't spend any time on this. But this is, I think, one of the first times this had been done in the early 2000s. What's maybe less obvious is that you can also do this to quite high charge, or azimuthal mode index. So here's an example, a zoom in of that. This is a scanning electron micrograph of the gold structure. And a focal series through the focus. And I'll just point out something a bit interesting, at least to me, is that we seem to see some splitting. It is already known from the many optical experiments. When you go to high azimuthal mode index, they're not always very stable, and any imperfections in the beam or in the illuminating beam, as well as the optics, can cause them to split into lower charge components, and probably that's what we're seeing here, as well as it going in and out of focus. Well, optics are just one way. Another way is to generate them directly. In the X-ray world, we use these devices called undulators, periodic arrays of alternating, typically permanent magnets. And they generate very bright beams, pencil beams of X-rays. And if you have a very small, low divergence electron source propagating through this, you get a very coherent beam coming out. So we took a look at this and predicted, in fact, that the high harmonics, where n is the harmonic number of this undulator device, from 2 on up, carry non-zero OAM, or L. And these are just calculations of that. These measurements have been done since. This was done at HCB in 2013, so a dozen years ago now, by Johannes Bartsch and collaborators. Other work by the Japanese followed up and did some very nice measurements in the EAV region, but it shows this works. So they did kind of a similar trick to what we did with the gratings, a helical undulator and a planar undulator, and interfered the two beams to see the evidence, in this case, of a spiral. It can be done also without a helical undulator if you get the electron beam spiraling through this device. But now there are many proposals. Hemsing et al. Has led most of them, but there are quite a few others to do this in XFELs in the future with an afterburner helical undulator at the end of a free electron laser, for example. Okay, so what can you do with them? As you know, polarized X-rays are sensitive to electron spin, or they can be, so-called circular dichroism via spin orbit splitting. And really this applies to core level states, the inner shells, I should say, the S and P levels typically, but it can go up to higher shells. This is an example in iron at the L3 edge and L2 edge, showing the difference in aligned spins or spins aligned with the polarization vector and anti-aligned, giving you a different signal. When you take the difference of those two spectroscopic measurements, you get the so-called dichroism signal, which is a direct handle on the magnetic state in the material. So I asked the question, and this has been out there for some time now, could there be an OAM analog to this so-called conventional X-ray magnetic circular dichroism? So we do expect dichroic effects when the vector potential A, which you normally can calculate matrix elements from in the Hamiltonian for this system, or any system, couples to electron spin. If we put in a Hamiltonian or a vector potential defined this way, which has not only the wave propagation term, IKZ, but IL phi in the exponent, and plug it in, calculate the matrix elements, you start getting some interesting results. You could imagine now, and I'll show you some plots in the next slide, measuring spectra with dichroism that depends on just this IL phi term, as well as a possible spin term with an OAM beam. So one could imagine probing higher order transitions than just dipolar terms, because L can be anything. Let's say 2. If S, the spin term, were 0, that might be a direct handle on a dipolar, perhaps even a forbidden dipolar transition in some material, a 3D to 1S, for example, in cuprates, manganites, ruthenites, and so forth. But there's a big caveat here, and I have to thank Kane. Where are you, Kane? Maybe he stepped in. He's here. Thank you for making this point several times. You see in this parenthesis term in the middle of the vector potential, rho over W, to the mode index power, L power. Rho is the size of the orbital you care about. W is the width of the beam. If the width is very big, or rho is very small, the effect is very small. So ideally, you'd like to have these about equal, or maybe the other way around, but not a big disparity between the two sizes. So that automatically, at least automatically made me begin to worry, could we have a hope of actually seeing these effects in electronic transitions where the orbitals are on order of an angstrom in radius? Maybe some large Rydberg system or something not, but it's maybe a guide to think about looking at larger things than simple single atomic orbitals. So I promised you some spectra. Here are some calculated examples in copper. In blue, we have just the unpolarized term E, the xy, or I should say the orbital term for L equals 1, and red, L equals -1, and just the normal dipolar dichroism signal, E, the xy, in it's black. It's hard to see these colors. But you see a difference, and you can imagine doing an experiment, for example, like this. This would be the conventional dichroism experiment, where we subtract spectra obtained with each helicity of polarized light, circularly polarized light, where S is +1 and -1, and in some transition metal, for example, at an L edge. Or we can do the orbital dichroism measurement, where we can turn S on or off, but more importantly, turn L non-zero, and do a measurement, for example, of a quadrupolar transition in this case, or even back to a dipolar transition where you compete with the S state. So now on to some, I'll just check my time here, on to some experiments. This is some really nice preliminary work that came out in 2021. The work was actually started earlier, and I'm hoping to hear more about this from Sujoy Roy later in the week. But they found a very nice work, a very nice result here that Woods published in 2021, where they could switch on and off with this magnetic structure here. It's an intentional defect drawn in permalloy. That's an iron-nickel alloy material to switch the OAM effect on and off magnetically. What you can do is organize the system. If you go above and below the antiferromagnetic phase transition, permanent magnet antiferromagnetic transition, to organize the spins to either cancel this out or collectively make use of this defect to generate an OAM state. What you see on the right are the Bragg peaks around the bright zeroth order at various orders, off resonance and on resonance. And you see clear evidence of these donuts. So they're just intensity patterns. We didn't measure the phase, but now I hope you're convinced that when you see donuts, you should start thinking about OAM with a clear intensity 0. This was extended just a few years later by McCarter et al., the same group essentially, led by Lance DeLong and Sujoy. And they now were able to probe, not just simply generate these states, but probe the antiferromagnetic state by OAM dichroism in this system. What you're seeing here is essentially what I showed you before, but now by a photoelectron electron microscope image, the magnetic and X-ray magnetic circular dichroism contrast, the magnetic directions in these states, and how this intentional defect drawn into this pattern can generate an OAM state and make these Bragg peaks, as you saw before. But now what they've done is go above the transition temperature at 380 Kelvin, cool it back down, and you see and the system coalesces back to a random antiferromagnetic state each time, maybe driven by local defects, but otherwise random, which you can then probe by conventional resonant X-ray scattering methods. So again, this was done at the iron L3 edge, where the resonance is most pronounced. Okay, quickly now, and I don't want to steal the thunder for the very nice talks to come, but I want to give those of you who may be less familiar with it some idea of the exciting work that's coming out just in the last 3 years. So we know now that orbital angular momentum can be imprinted on a single photoelectron. These are helium atoms photoionized by XUV pulses and illuminated, in this case, with an OAM imposed on the XUV beam and measured at Fermi at 24 or 28.5 eV. The signal was very clear here. This was published in 2020, but there are also hints back by Schmigelo in 2016, so it's worth checking the earlier publication. And we now know, in fact, I'm sure we'll hear more about it this week, that X-ray magnetic dichroism can be visualized by OAM directly in systems which have quite large magnetic structures compared to electronic orbitals, that is. So again, we're looking at permalloy systems, these so-called dots with a defect. We know from PEAM images, the magnetic structure looks something like this, with a defect in the center, and the contrast is quite evident by switching the orbital angular momentum between 0 and plus or minus 1, for example. Again, measured at Fermi, but now at 52.8 eV at this 3P to 3D transition. There's quite a bit of other work, but I'd like to just to share, but rather than, again, steal the thunder for the rest of the talks, I'd just like to give you some ideas for where we might go in the future. These are relatively simple, I would argue, topological states, really only utilizing so far conventional dichroism, but with orbital angular momentum, not quadrupolar contrast, for example, which would be much weaker than the dipolar one. And I should have mentioned, if we're doing some kind of spectroscopic measurement or contrast for a dipolar signal, sorry, a quadrupolar or higher order signal, we'd probably want to find a way to subtract or counterbalance a massive dipole signal on top of it. And it would be possible to get fooled, I think, if one wasn't careful with a very precision measurement. Nevertheless, more complex topological states one could probe. Skyrmion systems now are getting, and have been getting, a lot of attention over the last several years, since they were really discovered about 15 years ago. These are some early works by Uchida and Nagosa, but showing these beautiful magnetic structures which are on the order of nanometers to microns, well within the range of systems we can probe with a focused X-ray orbital angular momentum beam. So just a few examples here. They're more complex spin systems in iron germanium and iron bismuth, bismate. But we also might look at artificial or natural as well as artificial spin ices, for example, if we could go do this at low temperature. Multiferroics, ferroelectrics, and so forth, where systems get quite interesting. We do know these systems are chiral, and we can employ many of the methods that we heard about from Kane earlier. But in the X-ray region, coupled with tuning to resonances to exploit the best contrast. There's some other exciting hints for the future. It appears evident that OAM, at least from theory, is now behind much of the discussion in Rashba splitting in reciprocal space, in the block waves. So if there's a way to couple to that, I think we might have a quite unique handle to complement the very nice work done by ARPAS and so on in systems such as silver tellurium. Okay, just to wrap up quickly, we know we can generate, focus, and detect X-ray beams, and I'm really going over a huge spectral range, but extreme ultraviolet to quite hard X-rays, and arbitrary and very nearly pure states, particularly using optics. We can separate individual orders quite well from the other ones. These states coupled to matter in new ways with many more degrees of freedom than we thought possible before. X-ray OM could make possible, in fact, a new, I would argue, L+S spectroscopy. We previously, all our conventional CD is, I would argue, just S spectroscopy of electronic transitions, and also enable access to topological states and materials with completely new, unprecedented sensitivity and control. There are many new X-ray bright or ultra bright X-ray sources, either on the horizon or coming online now. MAX 4 in Sweden has been running for nearly a decade, but the ESRF UBS turned on 5 years ago, and now we have several in Europe about to turn online. The APS in Chicago has gone that way. We'll have ALSU in Berkeley, and so forth. And that can lead, I'm really certain, to unprecedented experiments that exploit these OAM degrees of freedom and their interactions in matter, or with matter. So thank you very much. I'd be glad to answer questions.